good afternoon, thanks everyone. So I'm Jinhu Lü from the Chinese Academy of Science. So this talk I will talk about the structure and function of the evolution complementary works. Okay, to start again, I would like to thank the organizers. So give me a chance to be here. And also, I would like to thank some authors, so such as Professor Ron Chen from the University of Hong Kong, and Professor David Hill from the University of Hong Kong, and Professor Benjamin from the Chinese University of Hong Kong. So this talk, I will talk some, to start with, I will talk about some background of this complementary work. And then the big data, so the opportunity and challenges for complementary work. And then talk about the control of complementary work. And then talk about the evolution of complementary work. And finally, I will give a brief conclusion. So, traditionally, complementary work are studied with graph theory. So there's a long history about complementary work. The famous model is Anderson Rendy, the AR random graph, proposed in 1960. After that, almost all the research focused on complementary work are based on the AR random graphs. Up to now, so I think 15 years ago, since about the availability of big data and super fast computing power, so let us to rethink about the ER random graphs. So before that, we cannot get the structured data or the dynamic data of the complementary work, and also we do not have the super fast computer. But after we got some data of the complementary work, and then we have the super fast compute power. So then we can use computer to calculate the structure or dynamics of complementary work, and then get some useful information. And this background, so there are two significant discoveries. So the first is 1998. 98. This is a small world, famous small world effect, and then the 1999 the circle-free phenomenon. So this is over the last few years, many research about complementary workers, focusing on some nonlinear phenomenon and control and the evolution of the complementary works are basically follow this line. So we have big data, and also we have the super fast computer. Normally we use these two tools. So one is the big data, and the other is super fast computer to get many information of the complementary works. So this is basically the idea of the complementary work. So now, in this case, I will quickly review the big data in the big data. So the big data promotes some opportunity and challenge for research in complementary work. So what's big data? So there is a Gardner hypercycle. So this cycle is reported on 2013. So there is a curve to show us the development of the big data research over the last, I think, 10 years. So also there are some typical events in this curve, so to show the development of the complementary work. So now the development of big data should be this step. So what's the big data? So we have the big data. Normally, the big data has four weight characters. The first character is volume. Volume is one large. So it's a big data, one large. And then increase very fast. So such as Facebook, every day there are some data, and also varies. So there are different kinds of data, and also the veracity. So some data are true, some data are false. So there are some are useful, some are noise, and many garbage data. So there are the mixing data. So this is the four Vs. And then I would like to give you some typical examples of the big data. So such as the custom transactions of the big company, and then science data. So the science data every day collect many data. And also the scientific research, such as we are to research in the biology system, and we get many data every day, and also social networks, and also web page, and also RFID, such as in every company. So there are typical examples of the big data. And then the big data, social is the word of networks, or word is the word of networks. And then the technical networks, big data. And then World Wide Web, and then financial networks, and then road networks, and then biological networks. So all networks join the big data. So this normally big data and common networks have a close relationship. So it's a bridge between the common network and big data. So also we would like to give examples on network growth. So such as big data. So there are many big data and many networks. In these cases, there are some existing solutions to manage network data, data. So traditionally, we transfer the live data to the live research space, and then we find there are insufficient memory, and probability, the high risk I/O cost. So there are many problems. So in these cases, so the data increase more fast than the increase of memory. So there are some problems to manage the big data. And also the data-centric technology. So the big data generate many chunks. And also the storage technology, we can say there are many massive parsing big data and data many grids and distributed file system and cloud computing platforms. There are many tools to deal with big data. So industry as a whole is worth over US $100 billion US dollar and grows almost 10% every year. So I will take this step, and then okay. So why we are interested in big data? So we should, since the big data has many applications in our world today, so such as health and well-being, environment and sustainability, emergency response, and disaster resiliency. So the recent example is the Malaysia airline events. So that's MH370. So we get the big data from the satellite, the problem is we cannot get the useful information from big data. So this is a problem. So, and also the transportation and energy. So, in the following, I will quickly mention some efforts in the world. So in Europe, there's the European Convention. So there is 2-year-long big data public privacy forums. So there are 70 framework program. So there is a program, and also there's the define research and innovation stage and guide the successful implementation of big data economy. So this is in Europe. There are some great efforts to do the research of the big data. And the big data in China, so last year there are two 973 projects about the big data. So we have the government programs. And then in NSF, there's the network communication and big data projects. And also the cyberspace security and big data. This is another 973 program. And also the government put 40 billion on the urbanization and the smart city. This is also a big data program. And there are also the other programs such as healthcare and big data in 863 projects in China. So basically, we deal with the big data. To make big data into small big data. So we can say the network of big data, everything network together, and the name abstract networks. So it's small networks, and then further abstraction, and then further abstraction, we get some useful information. So from the big data to the small data, we get some useful information. The problem is when we use some such scientific tools to abstract the big data, so we lost some useful information. Maybe we get this information is unuseful, is false, maybe false information. So sometimes because we get false information. So this is the problem for changing also the application dependence data characters. So such as the data and noise and unreliability and variability and accessibility and single modular and mixed modular, and there are many different characters. So property of the interest. So normally we use the macro level property, and then the macro level property, and then class level property, and finally the group level property. So if we have solution of the get some sparse and the quantity cannot be verified. So this is this application and requirement and the goals of big data. And then also the technology, you can say this is science and this is engineering. Now it's from normally we get some bridge from science to engineering. And also we find the more characters of big data, such as the diversity of application and diversity of the data property and diversity of goals and objectives and many other characters of big data. So we would like to try our best to get useful information from big data. This is some quick review of big data. So since there are normally there are many interests in big data. So in the following, I will talk about the control of common networks. So basically, regarding common level is based on recent work in this over the last few years. We did some research on the control of common networks. So for large common level, we would like to use some specific technology or theoretical method to control network to our intrinsic goals or some other properties. So regarding the control of common networks, so we can say we can discover so what do real world look like, and if we cannot accurately look like, and then modeling and then impact and then control. So modeling, impact, and control. This is for the control science. They are interested in the goal of the control can be achieved or by only direct control or flex of loads. So this is the control science. For network science, this is how to select the loads to be controlled so that the goal can be achieved with a lower cost. So this is the problem is the complexity of the network structure, and also there are some special issues on the control of the common networks. So for the large of common networks, it's often impossible to control every load. So since there are too many loads, we don't know, sometimes we don't know how many loads. So in this case, but it is impossible to control a small world of loads, such as 5%, to achieve the same effect. So this is possible. So we call this method is pinning control. We only use 5% loads control to reach the same goal. So this is change in common networks. So there are some earlier tests in this field, such as pinning control. Okay. The problem is, okay, for the pinning control common networks, so it depends on network structure. For different structure, we have two different methods, and the coupling strength, and the number of controllers, and the control strategy. Normally, there are many factors are trade-off issues in common networks. Also, the common networks are evolved with time, so this is another challenge. So in common network, there are two interesting questions. So the first question is how many and which nodes should the network with fixed structure and the coupling strength be pinned to reach network synchronization? So this is the first question. So you should have how many and which nodes. So this is the first question. Another question is how large the coupling strength should the network with fixed structure and pin nodes to apply to reach network synchronization. So this is the two chain problems. So we have some we get some main advance in this area. A simple approximate formula is deduced for estimating the detailed number of the pinning nodes and also the magnitude of the coupling strength for given general common networks. We have some recent work in this area, so to estimate the number of the pin nodes and the magnitude of the coupling strength. So in the following, I will talk about the evolution of common networks. So regarding the evolution of common networks, it's based on our recent work in this area. So the first paper is a recent review paper, just outlining our recent work in this area. So structure means function in evolution dynamics on common networks. So we will quickly review the background on motivation of this area. You show you well known the genotypes, the phenotypes, and the behaviors of the population are evolution with time. So there are three fundamental principles of evolution. So reproduction, mutation, and selection. So one interesting question is what's the population looks like in the end. So in other words, which type of the individual survives and which is inhibited. So the evolution dynamics work. So the evolution dynamics models the evolution process of the population. So there are two famous models, Moran process and rate facial process. So generally, a population with size n and two types of individuals, we call M and R, is clear. We can say this is the unconnected population, and it's connected with strong connected population. We can say there's some the evolving of the population structures. So different structures, we can say. So now we give some notations. Some notations. The constant selection, the fidelity of the mutants is set as R, and the random is set as I, as 1. So this is the frequency dependent selection. Every individual plays a 2 by 2 game, with all labels and the fidelity is divided by payoff. So this is the norm. This is the famous game, and then the birth death process. So we quickly. So at each step, with the probability population to be fidelity. So this is the birth death process, and also another process is the death birth process. At each step, a random individual is selected to die. So all labels computed with for the above locations and with the probability properties to its fidelity. A label wins the location and leaves an offspring there. So this is this is some notations. And link dynamics. At each step, one link ij is selected randomly, and then the individual I reproduce, and its offerings take over individual J. So now also the dynamics. After this rule, so we give some examples show us the program. So such as the first example is the BD updating. So we select this bird, this bird, and then randomly, this is randomly random death. So and then this is the VP reproducing, and this is BD updating, and this is IM updating. So to show us how the game works. And the evolution dynamics. So such as evolution, we have this structure, and then the mutations to this one, and then the evolution this one, the two agents, and then the evolution, evolution, and then this way, and then finally we get the structure of this, the whole that works. So this is another example is about reason and mutants. So this is middle process, and then evolution, and then evolution, and then evolution, and finally get this stage. So that's and also, but for the evolution, that makes uncomplex works. So in the beginning, I have this structure, and then there's more complex uncomplex works. So state translation, and then state translation, and then answer for this state or this state. So now we only consider the two possible states on the complex work. For each node, it maybe red one, or maybe green one. So there are only two choices for every node. So now when the game are come down, we get the final only two final states. So the problem is what's the critical probability of the evolution. So this is the interesting question. So the long standing open problem is for the individual with the higher fitness will have a higher survival probability. So the essential difficulty is the computation complexity of fixation probability. So this is the complexity problem. So it's challenging to problem this question. So our main aim is it aims at providing a rigorous theoretical proof for the global existence of such property in the local evolution dynamics by using the coupling and solution technology. We would like to give a rigorous theoretical analysis of this critical probability analysis. So we also proved the fixation probability is monotone increasing for the initial nodes set of the mutants. So we will quickly just mention this is the fixation probability problem. So we have just talked about this problem. The probability that the mutants eventually spread and take over the whole population. So this is a problem, the fixation probability problem. And then we will quickly reveal the proof. So mathematical distributions, and then some mathematical distributions. For case A, we have the result well-vaccinated populations. In this case, we have this serum. For the case B, the structured population. In structured population, the computation of the fixation probability has a very high complexity for complex works. So this is the difficulty. So how to prove the two basic properties for the evolution dynamics with structured population without computing the fixation probability. So the main results, the theorem, we prove the theorem, the fixation probability is monotone increasing with the initial states. So this is our main results. And the second result is regarding this is a fixing the probability is also very increasing with the mutants fitness. This case is regarding the artificially connected networks with DB updating rule. For different updating rule, we have different theories. So this is since the method different. So and finally we give a simple example to show us the numerical simulations of this the random for this case we can see some numerical simulations. There are for different fitness the fixation probability increasing morphology coding with the size of the mutation size. So we can say this is increasing with the size with the mutation size. So we can get and for the serum 2, we also have the examples. This is shown here. Finally, I think I have since the time limit we have to stop here. So normally, so for the result for future research, we just talk about some personal views. The first view is that our research is driven by the major relational structural needs, so such as smart grid for the Internet of Things, for the mobile Internet, and location-based service, and gene regular network, such as some. This is driven by the relational strategy, and the other is driven by the forefront of the international academics, so such as some intuition topics. But maybe it's a challenging problem in this area, and also many other topics. So thanks everyone.
Thank you, Okay, so there's any questions?
In your research, you consider the IC, you consider directional network. If you consider the unidirectional network, what is this?
So for you just regarding the difference for for direct network or indirect network is totally different. Normally, for the evolution of some network, for the indirect network is much easier, since the evolution they are only consider the how to say, so just the computer of the compute of the we did not consider the direction of the network, but for the direct network there are some spaceful routes, so this is, I think this is much complex, so this is challenging for our problem.
Yeah, thank you for a nice overview. That was enjoyable. I want to ask you two more or less technical questions. The first is just a question for my education. You mentioned the technique, I think you called it splicing technique, that allowed you to have a certain analytical derivation. Maybe you could just say a few more words about that. That's my first question. And the second question is, it is probably so that for many networks, and probably we can make that mathematically precise, the fitness of the mutant elevates the fixation probability of the mutant. I'm just wondering, I think it is also possible to construct counterexamples. Maybe they are a bit contrived, but I was wondering whether you have thought in that direction.
Okay, so thanks for the question. So regarding the background, so basically, my background is I got my PhD in applied mathematics. Then I work with Sam Lamin in Princeton University regarding the complexity of the biological system, and also there's some use mathematical tools to solve some biological problem. Then I moved to Royal Melbourne Institute of Technology. I got a professor position now. That's the electrical engineering, so the control area. So for my background, and then I back to China. So normally, my background is a big thing. So applied math and the control theory. So it's a big thing. I regard to the first question, and the second question, yeah, this is a very interesting topic to from different view to treat from different view to the problem in evolution dynamics. So for different views, we have different methods and maybe get different results. But regarding our just talk about the fixation probability of the evolution complex works. So normally, most results are based on the simulation, only simulation. They didn't all large fields. We cannot find any theoretical results in this area. So in this case, I asked my PhD student to focus on the problem to give a rigorous proof. So to get some the nonlinear phenomena over the complex. So this is basically our research. So thanks for interesting question.
Okay, I think we should move to our second talk.
Okay.
Thank you again.